Hey, welcome everybody. First, I want to make sure that everybody had a great, happy new year. 2020 sucked. There's no question about it. The worst year of all of our lives, I'm sure. I can't imagine too many people experiencing worse lives unless, they maybe lived through the Great Depression, World War II, those kind of things, Vietnam. But for many of us who aren't that old, what's happened in 2020 was some of the worst stuff imaginable. Comparative to even like 9/11 and Challenger disasters and things like that nature. So hopefully 2021 will be a lot better. It's got a low bar, so it only has one job: be better than 2020. But going into 2021, I kind of want to do more science stuff, more math stuff, more philosophy stuff. I know that's what the Patreons want. I've talked to numerous Patreons, and those support my channel. Those are the members of the channel. That's what they're here for, I think. A lot of them actually really like this stuff. They like listening to it. They like learning about stuff they haven't ever been exposed to before. I am the same. I watch those kind of channels where I learn things and I go, hey, I didn't know that before. Or, hey, that was really well explained. I'd never thought about it that way. Those are the ones that I really listen to more than anything else. I really think that, our dear friend Bullinator would have wanted us to try to continue on in some capacity. It's hard. It is difficult. A lot of people have been messaging me, how am I doing? How is everybody else doing? How are we going to make it through? And I have no real answers, to be honest with you. It's just we're going to have to try. We're going to have to try to continue on. And I think this is kind of a way to honor his memory. So hopefully I will do this justice. This is one of my favorite mathematical formulas of all time. It is called Euler's identity, and it comes from Euler's formula. I'm going to try to approach it from a very aesthetic point of view, meaning that the beauty of this formula, I'm going to show you kind of how it interrelates, hopefully, to many things that we talk about on the internet, Twitter and YouTube. There's some kind of like synergy between math and science and physics and all these different subjects we talk about. And they're interrelated, very much so. And I think that when people start seeing there's a beauty and a symmetry that exists between all the different topics, things start to fall into place. So first I'm going to welcome everybody out there. I see a whole bunch of people. Intrigued Feline and Cheshire, Icarus, Dr. Pi. That's not his real name, by the way. But some of this is actually based upon William Pi's work, Dr. William Pi. He wrote a guest blog on the Great Debate Community. It is in the video description. I've touched on that. I'm going to be doing a separate video on that particular blog. It's based on the hierarchy of sets, and it's going to be a whole different stream dealing with rings, fields, groups, things of that nature. This presentation is going to touch on it a little bit. And I've also have another blog that I wrote about Objectivism, I guess you can say. It's more along the lines of what's called Intensionality Matters. And I'm going to be doing that blog separately. I think maybe Cheshire might want to do a goblin read on it as well. I always find her reads to be on point, and I like the fact that if I can understand it and Cheshire can understand it, well, any of you can understand it. Let's be realistic. If Chesh and I can understand this stuff, then really nobody has an excuse not to be able to understand it. That's the way I'm looking at it, right? So, all right. So let's kind of dive right into this. Yes, the gang is all here. And again, I don't expect these things to get a lot of views. I want to make this very clear. And let me go on record. I don't do these for the views. I don't do anything that I do on YouTube for the views. What I do it for is I want people to watch because they're educated by it, they're entertained by it, they're informed by it. That's what like Caffeine Corner is about. For Cheshire to go on with me and talk about how to recognize certain patterns of behaviors, how to understand things that motivate people, how to understand concepts when it comes to critical thinking. That's all these videos are for. And if people want to watch them, great. If they don't, then they don't. But I know that the Patreons I have, which is my lifeblood, is my Patreon. And my members, those are the ones that, tell me what they like to watch. And I agree with them. This is what they like to watch, and this is what I'm going to do for them. It's definitely not for the views. But anyways, let's dive into it. Hopefully I won't make a mockery of it, because again, this is a lot more complicated than people might realize, but at the same time, it's so elegant that it's actually simplified. So what this identity is a relationship that contains some of the most fundamental things in mathematics. It contains constants, and it contains mathematical binary operators. So the reason why this is so elegant is because it could be derived eloquently from the unit circle, which I've got in the upper right-hand corner on your screen, which we'll get into. Just use it for reference, but basically it all boils down to that little unit circle up there. But it contains these following things. One, it contains a specific constant called Euler's number. And Euler's number is approximately 2.71828, 182845. I think it's 9045. And the only reason I remember that is it has to do with the right. I think it's the internal angles of a right triangle. I think it's 2.7, then 1828 twice, and then 45, 90, 45, if I remember correctly. But anyways, you don't have to memorize it that many decimal places. Now, people know I memorize pi to a lot of decimal places, like 3.1415926535887. I've got it down to like 20 decimal places. I've already done a video on that where I've actually memorized that. Don't really need to memorize Euler's number, but you'll see it crop up all the time. It's extremely prevalent in mathematics. The reason why it's prevalent in mathematics is because it's related to many different things. First of all, it is an irrational number. And what do we mean by an irrational number? It means that it cannot be expressed in the form of a fraction p over q. That's simply what irrational means. In other words, it can't be two integers and a fraction. Like 1 over 2 is a fractional number. So that is a rational number. So anything that can be expressed in a fraction p over q, where those are two integers and q is not 0, obviously, because as we know by other videos, dividing by 0 is bad. Bad things happen. We don't want to divide by 0. It also is the base for natural logarithms, and that comes in very handy in physics. Anybody who's ever worked with radiometric decay rates or any kind of decay rates or exponential growth rates, bacterial cultures, population growths, these are all contingent upon natural logarithms, and you'll see base E a lot for them. So it is a very prevalent number in physics. And then it's important to recognize that E does not terminate. This is a non-terminating number. It doesn't just end. 1.0 terminates, right? It has a termination. As we've seen on Twitter for the last, I don't know how many weeks now, people arguing, I call them, by the way, objective math deniers, OMDs. That's my term for somebody who basically will refuse to accept known mathematical facts even if they're proven. Like 0.99 repeating equals 1. People think that we go too much into that, but I don't. I use that as a litmus test because I had to think if people object to that, if people do not conceptualize that properly and refuse to accept it even after be shown actual mathematical proofs, they are not, in my opinion, critical thinkers by any stretch of the imagination. There's no critical thinking in them if they deny actual math. That to me is the litmus test that I use. I know it's sad because, why should one thing kind of determine whether somebody's a critical thinker? Because you cannot get any more objective than math. You can't say you're a critical thinker. You can't say you're even a skeptic, as they use the term skeptic, which I use it differently. But for the people out there, a skeptic who just doesn't believe everything, willy-nilly, that doesn't accept things at face value, like people's claims about supernatural and stuff like that. But you can't call yourself that if you can't accept mathematical facts. Because there's nothing more objective than that. A couple things as Dr. Pi points out. It doesn't repeat. I was going to note that actually. Those 3 ellipses at the end of that does not in particular mean always repeating decimal. In this particular case, it does not mean repeating decimal. What it means is non-terminating, and it goes on ad infinitum. It just continues. So there's no ending point in that number. When you calculate E, you only calculated a specific decimal point or decimal place. I think they've calculated up to 1 trillion or so, but it never reaches any end. So you can calculate as many decimal points as you want, but there is no last digit. It does not terminate. Unlike a rational number like 1/3, which does, it's not terminating, but it does repeat, right? So 0.3333 repeating, 0.9999 repeating. Those are repeating decimal expansion. It's called infinite decimal expansion. So this is an example of ellipses using as a symbol that means something different, right? So you have to be careful when you look at the symbolism using math. One size does not fit all. So just because you see those 3 ellipses does not necessarily mean that it repeats. It can also mean non-terminating, and it can also mean that something is missing. In other words, if you have a long number and you don't have enough room to put the entire number in there, you can put the dots in the middle between 2 sets of numbers, and it doesn't mean after infinity there's some number. It just means that there's something that has been excluded from your work because there's too long a number, whatever you didn't want to put in. So if I have, let's say I have like pi 3.14159, 265, 358, and I don't want to put in the, I have 3.14, but I want to exclude a whole bunch and then, go to some other part of pi. You could put the ellipses in the middle there. So, like I said, it can mean different things. I contains the imaginary number I. Imaginary numbers really do seem to confuse people. And I understand why. They're not easy to conceptualize. It really wasn't until I conceptualized them as considered to be something rotational, right? If you look at an x and y axis, that's 2-dimensional. You have your x-axis and you have your y-axis. And by the way, a lot of these things that I do will draw on other videos. So go to my playlist for my calc videos, and you're going to find us talking about these things before. So hang on one second. Okay. All right, so as a matter of fact, I got to put some links in the video description on that. But if you go to my playlist, I'll talk about all these other things. So the imaginary number so to me, it's like a rotation. So it's like a rotation on the x per se. You'll see it used in a lot of torque values. You'll see it used in dealing with a lot of sine when you're dealing with frequencies and signal processing. It's part of a complex number. So I is defined, literally defined, as a square root of -1. Matter of fact, I have equals square root of -1, but you can actually say it's defined to be that. Okay? So when you have a square root of a negative number, it doesn't have any real component to it, right? You can't find the square root of -1 because 2 positive numbers do not have a negative number. And if you remember from what I said before, all square root functions only produce a positive single number, okay? And so there's only one primary square root result from a square root function. Remember, a function is 1-to-1 correspondence. So if you put a number in, you put something in, you get one thing out. For one thing in, you get one thing out. So a function cannot have 2 answers to it. So if the square root function is a function, it can only have one answer to it, and that answer is always going to be positive. Okay, so yes, even though things like, you can times 2 negative numbers and get a positive numbers, when you're doing a square root, you only returns the positive number, always. Okay, yeah, and by the way, I'm going to do a separate video on rectangular and polar coordinate systems. That's one of the first things we had to do in nuke school was a lot of that stuff in A school. But that's going to be a separate video. But anyways, that's what I is. So when you see I, it is saying, okay, it is a square root of -1, which again does not exist in the reals. Number 2, imaginary numbers are part of the complex number. Okay, so all imaginary numbers are the imaginary part of a complex number. Reals are a subset of the complex numbers we're going to get into in a second here. But let's just dive into that. All real numbers are complex numbers, meaning that all real numbers are a subset of complex numbers. Now, this may not always hold true in some types of math. And I'm going to get flack for that either way. It's really going to depend on how you want to look at it. I look at it as real numbers are a subset of complex numbers. Okay, I think there is what's called an isomorphic or bijection homomorphism. And all that means is that there's a 1-to-1 correspondence between the real numbers and the complex numbers, and it's bijective 1-to-1, and it can go both ways. Okay, so for everyone going to one field, one group to another. So the reals correspond to the complex, and you can map them backwards as well. But you can also think of complex numbers as ordered pairs, and the ordered pair would be what's called a couple, and that's going to basically mean x, y. That's an ordered pair. So all complex numbers can be thought of ordered pairs. And by thinking of ordered pairs, they don't really map. Just say all real numbers are complex numbers if you're using them as sets. So you just got to be real careful, depending on what abstract algebra class you're taking. I've read up on this to the point where at least I kind of understand it, that if the teacher says, look, we don't treat real numbers as subsets of complex numbers, that's fine. It just means that they're looking at it as an isomorphism. And that's a fancy way of saying that you have some function that maps from one thing to another that keeps some kind of symmetry, shape relationship. So one of the examples that I'll use to describe this particular concept of isomorphism is, and this is fancy writing, but one of the reasons I do this is I want people to see the notation and not get scared of it. Because you see all these weird things in mathematics, and you're like, oh man, what do all these symbols mean? But when you start looking at the symbols, they're not as complicated as you think. Well, yes, they are, but you can break them down, right? Because I don't get into the complex stuff. If I can understand this, it's not that complicated. But what this is saying is that it's for a function as the natural numbers. This double struck is something that means the set of natural numbers, okay, will map to E as in the even numbers of the natural numbers. That's supposed to be double strike, but unfortunately the program I use doesn't allow for a double strike E. But if you see E, that's the set of even natural numbers. And this is saying that for every number you have in N, you'll see it as N as an element of N. For all of N, any number you pick, which is 1, 2, 3, 4, 5, these are natural numbers. 1, 2, 3, 4, 5, those are natural numbers. Any number that you pick, if you times it by 2, you're going to get an even number, right? So that little arrow symbol means that it maps for any natural number, any n in the set of natural numbers. You can map a one-to-one correspondence such that, in this, well, by the way, this is called set builder notation. X as an element of natural numbers, so any x in the natural numbers, which is divisible by 2, you can do this formula. Does that make sense? And the real, I mean, again, these are the ways of defining these things when you get into the crux of math, right? When you get into the heart and soul, the engine of math, these are how things are defined rather than just something superficial. Like, for example, superficially, everybody understands a function of x equals 2n. I mean, nobody understands. Well, actually, I should put this as an n, I guess, right? Because if I'm using f of x, I should have to use the same variable, right? So let me change that. All right, so f of n, 2n. So for any value of a function n, any number I put in there, 1, 2, 3, 4, 5, whatever, and I times it by 2, I'm going to get an output. If I put 1, I get 2. I get put 2 in, I get 4. I put 3 in, I get 6. 4 in, I get 8, right? And so it maps 1-to-1. A 1-to-1 correspondence between two groups that are of relationship like that would be called a bijection. And we're going to get into a separate video, I think, when it comes to bijection, injection, surjection. They're all interrelated, but I don't want to get into that right now. But just let's understand that you can take a function of natural numbers, times it by 2, and get a different set, right? So those are two different sets, which, by the way, have the same cardinality, but they're two different sets. And by the way, this is why, again, the elegancy of Euler's identity, because all this stuff relates to that. All this stuff relates to these types of concepts. You'll see the term homomorphism, which is basically an isomorphism that has a reverse function. So if you have a function where you have something that maps to, oops, you know what? I have this backwards. Teach me to do this. And I did this morning, by the way. Let me see here. Let me fix this. But I like this program because you can fix on the fly. Okay, so if you have a function where A maps to B and B maps to A, they call that a homomorphism. Again, just a term that you just be wary of when you see it out there. I don't want to get into too much detail on it, but you'll see these things come up quite a bit in topology. Okay, how you would actually show this would be the reals as a subset of C. This little formula that you see here, R is this little, and this little symbol like here, that means a subset, okay? So when you have the reals are a subset of C. So you'll see that a lot too. So again, these videos are just to get you to kind of expose you to the types of things that you'll see when you start reading about them. That's all. Not to have any in-depth stuff. It's just you'll see this seen as reals are a subset of C. That's all. And they're double struck, meaning that's a set. So when you'll also see them singular struck too. You'll just see R as a subset of C. But if you see this little funny line, you just know that you're dealing with a set. That's all. Now, when you have a real number and it's in the form of this A plus BI, you guys have seen that before. We've talked about it before. Real numbers are in that form, and real numbers are where you have B is 0, and B times 0 times I is 0, and you're just left with A, right? So the real number is in that form, which is a paired, but the imaginary component of it is 0. So you just have a real component. And you'll also see that with a funny looking R, it'll be, or a funny looking I. If you ever see those things, the funny looking R means it's the real component. The funny looking I, and I didn't put these in here, will be the imaginary component. Okay? And you also see that the complex numbers are defined by an ordered pair where A and B are elements of the real set. Okay? And again, you may see it listed like that, in which case it's not technically a subset of C from what I understand, but it really is how you want to define it. An ordered pair can't really be a subset. So if you want to define complex numbers by ordered pair, where an ordered pair would be A, B, or elements of the real numbers, or R, there's an argument to be made that R's are not a subset of C. So it's one of those things that you might see people arguing on the internet. Are reals a subset of C or not? The answer is it depends. I hold that they are, but it really depends. The second coordinate would be 0. Yeah. When you have right here, if you have some group that the reals is a subset of C, where you have ordered pair A or B for every A as an element of R, B would be 0. Right? So you have an ordered pair. Well, no. Actually, no. I don't think so. Dr. Pi, right? I don't think B would have to be 0. It's for any ordered pair. You can have a complex number for any ordered pair, but B does not necessarily have to be 0 as that ordered pair. I don't think so. It only is going to be if C is defined as an ordered pair as an element of R, isn't it? Let me get back to you on that. I again, trying to relate these to ordered pairs, a completed type of mathematics that I haven't really got into that much. When you start dealing with a different, I don't want to say axioms, but it's a different way of describing something. Describing a real number as an ordered pair is a completely different way of looking at a real number, right? I don't look at it that way, but that doesn't mean it's wrong. To me, a real number is comprised of basically a construction. Be it what's called a Cauchy sequence or a Dedekind. You can construct a real, but you can also use them as pairs in abstract algebra. Okay, so he says yes, but any complex number is AB, yes, but you are embedding the real number A into the complex field, which would be what, again, with this little mapping symbol is talking about. You're mapping from one field into another field. And the reals are a field, and the complex are a field. And we'll get into the nomenclature for a ring, a field, and a group when I do the video on Dr. Pi's blog that he did. It's not an easy read, but I think it's informative. It's not that. I mean, he didn't write it like super high level. He wrote it so people can understand it. But if you've never looked at ring theory, it can be a little daunting, I guess you can say. Yeah. Okay. Yeah, I may have messed that up a little bit. By the way, I'll fix that, Dr. Pi. If you tell me which one to fix here, I think it's the problem is here, right? There's no B for J to use. It's just the second line that's the issue. This one right here. C is defined by AB. It's just a minor typo. I'm not going to sweat it too bad. Again, I don't use that type of nomenclature too much. I just want people to be exposed to it. So when they see it and they see people say, well, R's are not a subset of C, they may be correct if they're talking about ordered pairs. That's all. Yeah. All right, so we got a ways to go here. We're just touching the surface of this Euler's identity. And that's why I think it's so majestic. Yeah, this second line. Yeah, I think you might be right. If I define it, but yeah, I think there might be an error in that. I'm just going to remove it from that. Well, I'll get back to it later. All right, you can annotate in the video description how it should be for me. I would appreciate that. All right, so all right, it contains pi. Pi is approximately 3.1415925. Again, these three ellipses do not mean that it repeats. It means that it continues on ad infinitum, right? And it's non-repeating, non-terminating. There's a question that people had asked Landon, I think it was on Cheshire's stream, about the normalcy of pi, whether pi is a normal number or not, which is a very complex question. There's no proof either way. I think that it's a normal number. It means that there's no real pattern in that exists in the number itself. I don't believe that the complete works of Shakespeare are encoded in pi, but that is nobody's proved whether it's called a normal number or not. Oh, he says, okay, so that second line is right. He says the third line, he says, it has an error in it. And that only because B should be 0, I think, right? Is that right? Should B be 0 here? I'm not sure. I think it should be B should be 0. Like I said, you put it in the video description. Again, pi is irrational, which again means that it cannot be described as a ratio of two integers, p over q, where q does not equal 0. P does not terminate, and p is finite. This is critical. A lot of people in these discussions keep on saying that pi is an infinite number. No! Say it with me now. No! It is not an infinite number. It is finite. It has an infinite expansion. But the number itself exists on an interval between two finite numbers of some kind, or pick any interval you want. That we have one. If you have one number less than 3.14159 and one number higher, that's an interval, and pi is somewhere in the middle. So if you pick the interval 1 to 4, right? Pi is in between that somewhere. It's on the interval 0 to 4. 0 is a finite number. 4 is a finite number. Anything between them must be finite. You cannot have an infinite number between two finite numbers. Matter of fact, in the reals, you can't have an infinite number anyways. In some other systems, you can. In p-adic systems, you can have an infinite number. You can have a complex infinity, which is a infinite number. You can have cardinalities like alpha null, which deal with infinities and infinite numbers. But for the reals, there is no infinite number. Okay, so that's wrong to say that pi is infinite. It's just not. And the only way you can actually prove that really simply is we all know that pi is a ratio, right, of circumference divided by diameter. So where did I get that C from? Where is that from? It's just a typo. Okay, so if you rearrange that, you get circumference equals pi divided by diameter. If the diameter is equal to 1, then C equals pi. So the circumference is finite. The circumference of a circle clearly is finite. You could, if the circumference of a circle was infinite, it'd be like the size of the universe if the universe was infinite, right? Right. So if you can have a circle and the circumference is something you can see, it has to be finite. So again, just when you see people saying pi is infinite or 0.99 repeating is infinite or 0.33 repeating is infinite or Euler's number is infinite, no, it's just straight out wrong. Yeah. All right. It contains 0, and 0 is a fundamental constant, right? So again, I'm just going to show you real quick. Looking back on Euler's identity, that formula there, right? Right? It contains a natural logarithm, Euler's number, actually. It contains I, imaginary number, pi, and contains two constants, 1 and 0, which I'm going to talk about right now. All right. So, yeah, and circumference equals pi times diameter if you just multiply that by both sides. Yeah, so simple manipulations. One thing of interest is odd is actually an even number. A lot of people don't realize that. 0 is even. Yes, it is even number. There's mathematical proofs for that out there and stuff like that, but just go with it. Yes, 0 is an even number. I've actually seen people say, well, 0 is not even or odd. Well, yeah, no, it actually is an even number. It will be in the set of even numbers. 0 is neither positive or negative. I don't know. I won that one. Fix that. Yeah, it's neither positive nor negative. It's unsigned. However, it can be signed plus 0, negative 0. And when you're seeing something signed, it basically just means that you're using it in a computer program of some kind, and there's a unary operator on it. That's all. But 0 under itself is unsigned. It's neither negative or positive. It's neither. But you'll see sometimes plus 0, minus 0 in computer programming, and that just means there's a unary operator that's being imposed on it to have what's called a signed. That's all. So again, computer programming, I love it when I talk to computer programmers. They have a completely different language out there, right? Because in computers, computer programming is a little bit different than like pure math. And you'll see things that you normally wouldn't see in a lot of maths because you don't normally see 0 being signed or not. Yeah, it's a multiple of 2, right? Anything that's a multiple of 2 has to be even. So 0 equals 2 times 0, which we'll get into that, which is going to be the multiplicative identity. So we're going to get into that in a few here. But 0 is called the additive identity. And it's kind of cool we're talking about identities because in the last couple weeks, dealing with some Ayn Rand objectivists out there, they love the word identity. And honestly, I don't think they know what it really means. I just don't. I'll get into what actually identity really means as we go on here. But an additive identity for the natural numbers, which is n, the integers, which is z, the rational numbers, which is designated by q, the reals, which is designated by r, and the complex numbers, which is designated by c. These are all, by the way, double struck. Means that there is something, like for example, in R, given in the reals, where R times R maps to R, and our functions where 0 is an element of the reals. And what that's saying is pretty simple. It's just saying that if you have two numbers in the reals, and one of them is the additive identity, then adding it to that will map to the reals. 5 plus 0 is 5. 6 plus 0 is 6. So that the 5 is in the reals, the 6 is in the reals. So you have two things that you're doing some kind of function to them. You're getting a result that's in the field that you're working with. So if I have a member or element of reals and I have some functions that are on it that are doing something to these numbers, and the output is a real number, right? Then 0 would be what's called the additive identity, that the number doesn't change. So whatever you add to 0, the number remains the same. That is actually what an identity is. Something that you can put in a value for a variable or formula or something that you can put in, instantiate with, and it doesn't change the output at all. And we'll get into that shortly. But I wanted to kind of touch on what do these things mean as far as why we have an added identities. You'll see them a lot in ring theory. And a ring is a quadruple. And by the way, these all relates to my word of the day stuff. Twitter. Every day I'm going to be putting out a word of the day on Twitter relating to math, science, or philosophy. Something that most people may have known what the word means per se, but maybe conceptually wise needs to be tweaked a little bit, or maybe they have a better way to understand it, which I find to be very challenging to do in 280 characters. I'm going to try to get into one tweet, but if not, we'll talk about them in multiple tweets. But today was tuples. Even though this particular presentation doesn't deal directly with tuples, it has a tuple in there, which in this case is a quadruple, meaning it has 4 elements to it in what's called a sequence, in an ordered sequence. So XY is an ordered pair. That is a couple, right? 2, right? Couple. So tuples. So you have a couple, you have a triple, you have a quadruple. These are tuples. So n tuple is anything that's greater or equal to the 0. You can have it as a 0 tuple, but that's just called a null set or an empty set. So in a ring theory, you have a quadruple with four things. In this case, it's the reals. You have addition, you have 0 as the additive identity, and then you have some binary operator. In this case, it's going to be a multiplication for the reals. Okay, so again, I will get into that when we do Dr. Pai's blog post that he did. Or he wrote a blog that I put on my Great Debate community as a guest post. You also see a lot of this course called Abelian group. You'll see that come up an awful lot. But an Abelian group is basically like the reals. It has addition, and it has some kind of additive identity. In this case, the additive identity for the reals happens to be 0. For other types of groups, it doesn't have to be 0. But for the reals, it is absolutely 0. And you'll see this in the form of some group, some commutivity. And commutivity means that if you have x times y, then y times x is the same thing for all x and y of the group. Okay, so commutivity is one of those things that's property of math. So 1 times 2 is the same as 2 times 1. So anything you put in for x and y, anything you instantiate those with in that group, the commutative property holds. So 0 plus 2 is the same as 2 plus 1 throughout the entire group. So when you get into these types of abstract mathematics, and the reason I'm touching on it now, you might think, what does it have to do with Euler's identity? Well, it really, a lot of this does. But we're going to be touching on why these numbers, like 0, is so important, because 0 is in Euler's identity. Well, 0 is an important number in creating mathematics. It's part of Peano's axioms even. It's a very important number. And when you get into the construction of rings and groups and fields, you'll see 1 and 0 come up an awful lot. Matter of fact, you actually see something called 0 equals 1, which is the 0th ring. And people's like, well, how does 0 equal 1? Well, because you're not actually talking about the value of 0, 1. You're talking about the additive identity equal to the multiplicative entity. So again, if you see 0 equals 1 in ring theory, it means something. It has a meaning. There's equivalency there. Equals still means equivalency. Contrary to what I've been dealing with these Ayn Rand objectivists, which I don't think, again, they understand equivalent classes or equivalent objects or equivalency at all. There is a relationship between these types of construction of mathematics that's extremely important when you have commutativity and associativity and properties. So this is like I said, this is kind of a really quick, basic introduction to why I think Euler's identity having 0 on it is so amazing, because of the symmetry between that and group theory and ring theory, which, by the way, I never studied. Never studied it. I've looked into it many times over the years, but I never formally took ring theory. I would have died. I definitely would have died. All right. Somebody says Steve has lots of calculus on his channel from a long time back. I'm guessing his major. No, I did take calculus in college, but that's not my major. Actually changed in college. I don't even like to discuss it. I actually went from physics to to accounting. It sucked. Accounting. Yeah, I hated accounting. All right. So. Okay, so E here, by the way, E here, and I put this in for a very specific reason. If you look in the form here where it says G star E, where G is a group, C is commutative property, and E is not the same as E up here. And I did that on purpose, just to show that a single unit like that, a single representation, a single signifier, so to speak, these are actually signifiers, doesn't necessarily mean the same thing in different fields of math or in anything, right? You have to be very careful when looking at something. Try to look at it from the point of view of what domain of discourse are you talking about. E in the domain of discourse for natural logarithms clearly means Euler's number. But E in something like ring theory doesn't mean that. It actually means the additive identity. And the reason why it's defined like that, again, these are how numbers are built. This is how fields are built. These are how rings are built. It's defined to be, okay, let's say I have some group, N, okay, which is going to be, in the case, natural numbers. That's part of R that has the additive binary operator, addition, right? That's addition. And then it has some kind of additive identity. In this case, 0 is the additive identity. It's a closed group, and all that means is that it's closed such that you put something in, it's whatever you get out, it's going to be in the same group. Okay? Really easy way to understand it. That's how I understand it. If it's closed under something, it just means that closed under addition means that whatever you add to it will still be in that group. So any element where you have E is an element of N, whatever group N is, whether it be the natural numbers or any group, such that for every N in N, any number, 1, 2, 3, 4, 5, 6, 7, in the natural numbers, you have this relationship. N plus E equals E plus N, because it's commutative, equals N. The output is what you put in. This, by the way, is what's called an identity. This is when I hear people on that thread, people know what we're talking about if you've been following Twitter, if not, follow me on Twitter. But people that are using the word identity, I don't think they understand what it actually means. This would be a perfect example of what identity means, is that for whatever I instantiate N with, whatever I put in there, I'm still going to get N back, right? Because adding 0 to anything gives you back the original value. This is an identity. So for natural numbers, for the natural set, right? N plus 0 equals 0 plus N. They're commutative, equals N. That's pretty simple, right? That part is simple. Yeah, I'm sorry. You're right. The natural numbers don't form a group. They don't have an additive inverse. Yeah, I apologize for that. And that's true. Yeah, I'm a little loose on my terminology there. But yes, the natural numbers do not form a group. But a group is defined by this, and this is not natural numbers. This is some group N. Yeah, I probably should have used some different group, like G or something here, to be a little less confusing. But again, I guess it goes back to, because you'll see it written like this, but it's not talking about natural numbers in this particular case. It's just talking about some group N, right? So, yeah, you know, to make it less confusing, because I don't want to confuse people, because they're right, because the natural numbers is not a group. Let me change that so it's a little less confusing, maybe. We all learn as we go here. So let me change it to G. Let G in E and G for every number. Is that better, Dr. Pi? I just call him Dr. Pi. Is that better? I think that's a little bit better, less confusing, right? Oh, yeah, you could use integers. Yeah, but I'm just going to put it as any group. G for group. It makes sense. Does that make sense? Let any group for R, whether you have addition, the additive identity be a closed group under addition, where the additive identity is an element of the group, such that for every number 1, 2, 3, 4, 5 in G, you have this identity. Simple as that. Let me know if that works for you, Dr. Pi. And I love the fact that I have him like checking my work. That's what I love about our community. People that know. I'm going to avoid cursing. I'm going to avoid cursing this year as much as possible. I know it's not going to last, but I have a tendency to demonetize my videos pretty quickly. And yeah, it's a rough year. So like I said, I'm relying on my Patreon. I'm relying on my member benefits. You know, or members memberships. So I'm gonna try not to curse. Let's see here. All right, so moving on here. 1, again, going back to Euler's identity, is a fundamental constant. It is that's an odd number. What am I thinking here? Why do I have even? That's crazy. Let me fix that. That's bad. Yeah, it is an odd number. There we go. I don't know how I messed that up. All right, so 1 is an odd number. It's also the first counting number called cardinal numbers. If you see cardinals, cardinal numbers are counting numbers, 1, 2, 3, 4, 5, as opposed to what's called ordinal numbers. Ordinal numbers would be something like a first, second, third, right? The order of something is in first place, second place, third place. When you see ordinal numbers, think of order. Cardinal numbers, think of counting. So 1 is the first counting number. And if I remember correctly, I think alpha null is the first counting of the infinite cardinals. I think it's the first infinite set is alpha null. I think that's how it's represented. Yeah, G, it'd just be some arbitrary additive group. Yeah, thanks. All right. All right. 1 is the multiplicative identity in the set of n, set of z, q, r, and c, which is, again, the natural numbers, the integers, the rationals, the reals, and the complex. And you might actually find sometimes like there's special notation. Like if you see z with a little plus sign, that means the positive integers. Z minus would be the negative integers, right? So you'll see those every so often. So for every n, every x that's in n, again, you could use n as well. It's not that rigid, but I'm just using x here to change it up a little bit. So e times x equals x times z equals x. Again, it's commutative, right? There's a community property here. So the order that you multiply makes no difference. 2 times 3 is the same as 3 times 2, right? Right? For the multiplicative identity of 1, 1 times 2 equals 2 times 1, which equals 2. So what you put in is what you get out. The actual, I guess, definition of identity. It's a little more complicated than that when it comes to identities. Technically, in some forms, when you're dealing with unit matrices and unit identities of matrix theory and other things. But for all practical purposes, think of an identity as just basically whatever you put in, you're going to get the same thing out. That makes it an identity for any values you put in. And you know what? I'll talk about this for a second here. If you go to that unit circle that I have in the above corner, let me blow it up a little bit for you, just real quick. This is called a unit circle for a reason. It's a unit, which is identity. Because for any x and y on the circumference, the radius is always going to equal to 1. And of course, you can get into the whole triangulation factors and right triangles and the unit angles and all that other stuff. But I just want to show that for any ordered pair, x and y, that's on the circumference, r is always going to be equal to 1. So it's a unit circle. It is always equal to 1. It is identity. As long as x and y are on the I guess it'd be the domain of whatever it is you're working with. As long as that's in the domain of the formula, then you're going to have a identity. So in this case, the domain is the circumference. Anything that you put in the ordered pair x and y in that domain, you're still going to have 1 come out of it for the radius. Okay, so that's why I wanted to show you that real quick. That's why I have it up there. All right. All right, so for any x that's in the natural numbers, 1 times x, commutative, x times 1 equals x. Simple as that. That's all it really means. Now, q, which is the rational numbers, is not closed under multiplication. Besides Dr. Pi, who can tell me why the rationals, q, the set of q, is not closed under multiplication? Let's see who can remember what we've talked about before, just intuitively from what we discussed. Figure out why the rational numbers, which is, again, p over q, hint, p over q, is not closed under multiplication. Again, Dr. Pi can't answer that question. He's barred from it. But see if anybody else can. Tell me why you think that q is not closed under multiplication. All right, so here's a more formal definition of identity. Again, I've just made it more succinct. I got this right pretty much off Wiki, but I've just changed it to be a little more succinct. But identity is for any equality that relates mathematical expression A and mathematical expression B, such that it produces the same value for all values of variables in a certain range of validity. So, in other words, you can only have certain numbers that can be put in, but in that range that you can put in, Right? I should call it a range rather than domain. Yeah, the range is what you put in, the domain is what you get out. But whatever values I put in, I will have the same thing out. In other words, A equals A is an identity. Why? Because whatever you put in for A, you're going to get the same thing out. I put 5 in, I get 5. I get car in, I get car. If I put in, 0.2, I get 0.2. What, right? No, Darth. Rationals are not closed into multiplication. It's not because 1 over infinity is undefined. 1 raised to infinity is not actually something you can actually do. Infinity is not a real number, right? So you cannot use infinity with any kind of operator. Now, think about it as a binary operator can only be used on something that has 2 real numbers, right? 1 plus 2 is a binary operator. It operates on 2 things. Infinity is not something you can use with any kind of operator because it's not a real number. So when we say something like 1 raised to the infinity, that's called abusive notation. In other words, we're trying to kind of heuristically get a point across, but reality is you cannot take 1 and raise it to infinity. It doesn't make mathematical sense. It's just an abusive notation to get a concept. Yeah. No, I'm sorry. Not closed under division. God dang it. I'm sorry. You're right. Let me fix that. Not closed under division. They are closed under multiplication. They're not closed under division. Let me fix that. Oops. I had a neighborhood flub. See, that's what I like about math and it's objective. When you make a flub, you can actually fix it. You can actually see that it's objectively wrong. So let me fix this real quick because it's supposed to be a division. I don't know why I put multiplication. Now I got to find it in my thing here. Here we go. All right, let me fix this. Division. Okay, now that's fixed. Yeah, it makes the most sense. Yes. So rational is not closed under division. And again, this is great because I don't mind making mistakes. It happens frequently. We all do. But one thing I like about math is it's subjective. It's not subjective, right? It's objective. If somebody says, hey, look, you made a boo-boo here, they can objectively show that you're wrong, right? And if you understand math, it's oh, wait, yeah, you're right. Shoot, I made a mistake, right? All right, so let me try that again. Why are the rationals not closed under division? Yeah, makes more sense now, doesn't it? Exactly. Yeah, that was a test. I didn't make a mistake. I'm just testing you guys. You guys all passed, by the way. Good job. Good job. I'm proud of you. Keep you guys on your toes. But now you guys got to answer why is the rational not closed under division? Again, it's not really that hard. Even the people that don't know math. Why would you think that if you have P over Q, that the values that you put in will not necessarily give you something that's a rational, or give you a rational number? Rational not closed in division. That is because 0 is a rational number and you can't divide by it. Yes, that is exactly correct. P over Q, where Q is 0, does not work, and therefore it is not closed under division. Yes. Very good. All right, so going back to some of the examples of identity. Because again, going back to that group, I'm telling you, oh, poor Cheshire. I don't know if she's watching, but if she is, give her some love, because she's actually starting to read Atlas Shrugged by Ayn Rand, which is the worst book that I've ever read. I don't remember if I even finished it. I think I got like 90-something% done. I was like, I recall I was so flustered by it, I don't even remember if I actually even finished it. I think I got 90% done. But yeah, it's just a horribly written book. And she's been listening to like audiobook or reading it, trying to digest Randy, Ayn Randian, and what do you call it? Randianism, I guess? I don't know. Of her objectivism nonsense, which to me is really just pop psychology, recycled pop psychology. Nothing is innovative. Nothing is novel. She just regurgitates things in a different way. Some of them are just, yeah, okay, sure, it's true. But yeah, I don't think she was any kind of real deep thinker. But if you saw Cheshire do her video today, her spasming motions, she said she was playing some kind of game called Beat Saber. I think that was just an effect of her reading Rand myself, but whatever. Yeah, well, the whole book is about like anti-altruism and selfishness and Yeah, it's just a terribly written book. But anyways, all right, moving on. So the next thing, we've all seen a lot of this come up when it comes to algebra, right? We just have a plus b and you square it and you factor them out. You get a squared plus 2ab plus b squared. That is identity. The reason being is for whatever you put in a or b, that relationship always holds. Hey, cool, identity. Another one that you'll see a lot using with unit circles, there's a couple of different Pythagorean identities, but one of the Pythagorean identities is this relationship here. Cosine squared theta plus sine squared theta is equal to 1. Again, that goes back to the unit circle. You'll see that come up where the radius is always going to be equal to 1 for theta, when theta is some angle on that circle. So if you take the angle and you take cosine square of that angle and you add it to the sine squared of that angle, you're always going to get a radius of 1. Okay, and when we get into polar and rectangular coordinates, I think I'll dive into that more. I've even got to brush up on a lot of that stuff. Trig was my bane. Yeah, trig was my bane. But again, when I say C unit circle, I'm talking about this up here, this unit circle. When you take the theta, which is again an interior angle in this particular case, and you apply cosine squared plus sine squared, you're going to get r equals 1. That means that is a unit circle. That's why they call it a unit circle. Unit for identity. All right. Whew. We still got a little ways to go here. All right. It has 3 basic operators. Addition, which is the inverse of subtraction. Has multiplication, and going back to Euler's identity, has multiplication, which is the inverse of division, and has exponentiation, which is, I'm going to explain it this way, but I got to tell you, and the reason I'm doing this, I'm not a big fan of thinking of exponentiation this way. I'm just not. I think while it is true, I think it really conceptually and visually confuses people when you're dealing with visual representations, dealing with 3 to 4 dimensions. But it is true that b raised to the n is just b times b n number of times. Okay? So b squared is b times b, right? We all know that. But just 2 dimensions. B cubed is b times b times b, which is cubed, which is 3D dimensional. And then b to the 4th would be b times b times b times b, which is 4th dimensional. But there's a problem there when you start dealing with space-time, because you're really dealing with 3 spatial dimensions and 1 temporal dimension. And I think it's a little confusing when you start talking about exponentiation as far as visualizing it that way. But we'll leave it at that. Okay? We'll leave it at that. But I did want to note that exponentiation is not commutative nor associative. And that's really important, right? Because the whole thing about multiplication and addition and things of that nature having these properties of math, exponentiation doesn't have them. 1 times 2 is the same as 2 times 1, right? So multiplication has these properties, but exponentiation does not. That's why another reason why I don't like to think of it as just repeated multiplication. It doesn't get those concepts across. Maybe that's just me. Okay, but whatever. I'm the one doing the presentation, so. But if you think about it, 2 raised to the 3rd, which is equal to 8, does not equal 3 raised to the 2nd, which is equal to 9, right? So clearly it's not commutative, right? And again, 1 times 2 is 2 times 1, commutative. But 2 raised to the 3rd is not commutative to 3 raised to the 2nd power. Yeah. All right. And it's not associative. So associative would basically mean 1 plus 2 plus 3. You can group them as 1 plus 2, or you can group them as 2 plus 3. You're going to get the same answer, right? That's associative. But here you have 2 raised to the 3rd raised to the 4th is not equal to 2 raised to the 3rd raised to the 4th. So if you change the grouping, you're going to have a bad time. You don't want to change the grouping when you're dealing with exponentiation because it's not associative. Yeah, matrix multiplication isn't commutative either. Matrix multiplication is a completely different thing. I think I did a video on matrix, didn't I? If not, I was going to. I have a presentation somewhere I was working on it, so I think I did. But I got into a little bit about matrix multiplications, dealing with rows and columns and 2 by 2 and stuff like that. But I really wanted to get into matrix more, but I did one on Compton's or Kramer's rule. I did one on Kramer's rule, but I didn't do a video yet on the additive inverse matrix, the identity matrix. I haven't really done one on mapping and transmutation. Basically, when you have linear equations and you want to manipulate them, to transform them, and how they kind of manipulate it into a matrix. I kind of want to do a video on that one of these days. I haven't got that far to do a video on that, but I think I might, because I think when people understand, when you're really dealing with 3 dimensions, X, Y, and Z, you have some kind of manipulation such that you transform them on the x-axis, the y-axis, the z-axis, what's actually happening. That is how it's expressed in the form of a matrix. And you do a lot of that in tensor mathematics. All right. Now we get to the good stuff. We just got started, by the way. This is not much longer, but here's where the meat of it come in. Now, for those of you who have not seen my video on Taylor series, Calculus 2, this is going to suck for you. See, you should have watched my video. Because this is how we derive, well, there's a formula now where there's identity. Here you go. Oh, what fun. Oh, what fun. Now, I don't really think I want to go through all this in detail, because I have a whole video on Taylor series already out there. And like a dummy, I forgot to put it in the video description. So I will do that when the video uploads. But be sure to check it out. If you're not too lazy, go look at my playlist. Look under Calc 2 Taylor series. But I will briefly explain it here, obviously, because it's part of this video. But I go into great depth to explain a Taylor and Maclaurin series in that video. It's one of my favorite videos. So this is where mathematics comes in to be fun. Yeah, you don't need to use a Taylor. This is just one way. I don't know if Euler did it this way. I think that he did, but there's other ways to derive Eulers. But this is one way. All right. All right, so what this is saying is f of x is equal to the summation of x of n to 0 to infinity. These are called the indices. Zeros, you can start your indices at 0. So it goes 0, 1, 2, 3, 4, all the way up to infinity. Now, I don't know why in this particular program it puts them out to the right, justified. That's fine. I mean, nothing wrong with that. This is perfectly fine. I'm just more used to seeing it, n equals 0 as underneath the summation and infinity above the summation. But this means the exact same thing. Okay? So you start off with a summation and you incrementally increase n from 0 by 1 every time. It's the counting numbers, but you're starting at 0 as your indices rather than 1. For f raised to, and by the way, this is not an this is where it gets confusing. This is not an exponent here. Again, know your notation for what you're dealing with. This is dealing with the first derivative, second derivative, third derivative, fourth derivative of a function. Then times a over n factorial. So if n equals 0, then it's 0 factorial. If it's 1, it's 1 factorial. Times the quantity x minus a raised to the n. Okay. Now, you'll find that in a Maclaurin series that a equals 0 and you just end up with x to the n. But I wanted to do the whole Taylor series. But this is important because n equals 0 is the function, right? For any function, you have f to the 0. It just means that it is the function. If it's to the first, you're talking about the first derivative, or f prime. If it's f2 or f double prime, it's a second derivative. And when I do a video on kinematics, we'll get into first and second derivatives for position, velocity, with respect to like a movement of projectiles, right? You'll see a lot in that kinematics, how a projectile moves with displacement. You know, you have your position, and then you have your first derivative, your second derivative, you're all the way up to, you know, what's called a jerk, which is your fourth derivative. And then you've got what's called snap, crackle, pop. I'm not making this up. Those are the actual names. Snap, crackle, pop. Look it up if you don't believe me. But those are the types of derivatives. So, again, not the point of this video is to rehash what a Taylor series is, but just know that the n here is not an exponent, but a type of notation for if that is a function, if it is the first derivative, second derivative, third derivative, etc. So when you expand this out, when you expand the summation out, you get f raised, f, which is just a function, a over 0 factorial, because when n equals 0, right, you have 0 factorial. And since f to the n here, again, not exponentiation, but f0 is just your function, you just have for the function of a times x minus a raised to the 0th power. Okay? And then moving on, the second time you add a number to 0, n equals 0, add a number 1. So 1 factorial. Then you're dealing with your first prime or first derivative. 2, you're dealing with the second derivative. 3, you're adding the third derivative, right? Because as n increases, you're taking a derivative, first derivative, second derivative. And then when you simplify that, right, you just end up with the function of a, first derivative of a over 1 factorial x minus a to the first power, plus the second derivative, a over 2x, x minus a to the second power. That's how you would expand this formula out. Now, again, don't really have to get that much in detail on it. If you want to know more about it, watch my other video. But it's important to note that this is how you can derive the Euler's identity. Okay. Now, since we know how to do an expansion, Taylor expansion, if I gave the formula for figuring out how to calculate n to any specific length, I could use this. The summation of n equals 0 to infinity, x to the n divided by n factorial. Now again, you can't actually do an infinite number of things in finite time, right? So if I tried to do this manually, it would never work. All right, so what a summation allows you to do, sorry, I had a message I had to get. What a summation allows you to do is do an infinite number of things all at once, right? You're just basically saying, if I could do this an infinite number of times in finite times, what would I get? So if you expand this out, e to the x is equal to, remember this formula up here, 1 plus x, e to the x over 2 factorial. You know what? That should be down here. I want to make this look right. That needs to be down here. And that's easy enough to fix. Well, I love this program. Wait, am I not on the right thing? Yeah, here we go. There we go. That should be the right one. Nope. Yeah. Is that it? One sec. Oh, that's down here, but I gotta fix that one too. I'm just grouping so it's easier to read. Give me 1 second here. All right. No, I still gotta fix this. There we go. On the fly changes. By the way, I use LibreOffice Math, but you can use other programs that are very similar. Okay, now it's fixed. All right. So this is what you're going to get if you put it in this equation. That's all. You can believe me on it, or you can do it yourself. But it basically you're going to end up with 1. You're going to end up with x. Then you end up with x squared over 2, x cubed over 3. That's all. As a matter of fact, if you wanted to show these, you could. This is actually over 1 factorial, which is equal to 1, and this is over 0 factorial, which is equal to 1, right? That's why you can simplify it that way. I mean, I can put them in there just if you want to conceptualize it, then it would look like this. 1 over 0 factorial. And then x over 1 factorial. Now, if you guys remember, 0 factorial is just defined to be 1. Now, there is a lot that goes into that, but 0 factorial is equal to 1. 1 factorial is equal to 1. So that's why you end up with just 1, because 1 divided by 0 factorial is 1. X divided by 1 factorial is x. So what Euler did was this. Euler said, okay, I've got this expansion for e to the x based upon my Taylor series. He's going to put in an imaginary number. And what happens? Well, you end up with 1 plus 1x I times x squared over 2x, I squared 2 cubed or 3 factorial, etc. You just end up, you're just putting an I next to the x. That's it. That's all you're doing. He's just sticking an I. So I to the x is going to factor to this, right? That's all there is to that. But here's where it gets interesting. You know what? Let me make sure I'm looking at my live chat here one second. Okay. Here's where it gets interesting. We know that I is the square root of -1. So if that's the case, then I squared must equal -1, and I cubed equals -I. If you get confused on that, which I always do, and I always will, there is what's called a Cayley table. And a Cayley table looks like this. Let me see. If you look on the little bottom right of the video, I just put a Cayley table out. I'm going to expand it up. And basically, this is a way of looking at, on the top row to the columns to the rows, if I have 1 times 1, it equals 1. 1 times -1 equals -1. 1 times I equals I. 1 times -I equals I. And you just basically will take your row and match it to your column to figure out what the result's going to be. So if I look, by the way, if you notice the diagonal is always 1, that's an identity. If that diagonal that goes down, that's always going to be 1. And then you see J a lot for electrical engineering and K a lot for electrical engineering. They're the equivalency of I, but they're also a little bit different and used for electrical engineering and orbital mechanics. But they're very similar. You'll see them in octonians and what's called, I think they're quaternarians, or however they're pronounced. But if you're ever confused, you can say, okay, what is I times I? Well, I times I is 1. What is -1 times I? Well, it's -I. So if you get confused, you can use that table to figure out what it is. But to kind of conceptualize it, to show you how I think of it, is this. I cubed is I times I times I. Okay. Well, if I substitute I, what we know it is, it'd be square root of -1. For the first two, okay, then I end up with square root of -1 times square root of -1 times I. Well, the square root of -1 times itself is squared times I. And what happens when you square a square root? It goes away, right? It just cancels each other out, right? The square root goes away because you're squaring a square root times I. So I'm just left with -1 times I, or -I. So this shows that I cubed is equal to -I. That's all this does, right? All right, so given that fact, going back to our Taylor expansion for e to the ix, he basically just grouped them. He said, okay, I'm going to stick in I, I'm going to group them. And what he did by grouping is he took every alternate one, where you have 1 minus x squared over 2 factorial. And yeah, let me fix that too. I don't know why that got messed up. It was right a few minutes ago when I was doing this. But it's easy enough to fix. I just have to manually go in and group them so it looks right. There we go. And 4 factorial. I'm just fixing the denominators because I don't know how they got messed up. They were all right before, but I'm just going to manually group them so I don't have that problem. That is one thing I like about this program. Like I said, you can just on the fly auto update it. Yeah. There we go. All right, that should be updated. Then I messed up something down here. Where I messed that up. Well, I'm gonna have to fix that because I don't know where I messed that up. Let's see here. group. Yeah. Oh, wait. Yeah, it's similar to latex notation, but I don't know where I messed that up. No, it's not there. Because this see how it says here is looking for input. Normally I could click here and it actually takes me where it's supposed to be. All right, let me just do this thing. All right. All right. Well, that just drives me nuts, though. I want to have that factorial down at the bottom there, and every time I try to fix it, it messes everything else up, and I'm not sure why. Is this it? Is this my little error? That's one of them. All right. Well, I'll figure out the grouping, but it's no big deal. All right. So he grouped it as 1 minus x squared over 2x plus x to the fourth over 4x. So every alternate one. So he took this one, he took this one, he took this one. And then the second group, he took all the ones with the I. So ix cubed over 3 factorial plus ix to the fifth over 5 factorial. Again, this is a minus sign because of going up here. E to the cubed is minus I. So you ended up with two groups. Now, the interesting thing about this is that these two groups actually are two Taylor series in themselves. They are the Taylor series for cosine x and sine x. And again, I don't know why all these factorials came out. They were just fine this morning. I did one thing and they all went to crap. But I'm fixing them right now. There we go. All right, so now you can trust me on this. I put the proof on the bottom, and I'll just kind of show it when I'm done. But for now, just accept, because I don't want to go into going into how to derive these Taylor series. But cosine x, this is the Taylor series for cosine x. This is the Taylor series for sine x. Actually, this one, yeah. And the interesting thing about this is that because when you put the imaginary number in there, e to the ix, he ended up with cosine x plus I sine x, which is known as Euler's formula. And that gives me an exponent. Easy fix. All right, there we go. All right, so this is where he got that from. He basically just factor these out and you end up with cosine x plus I sine x because the I is factored out here, right? So I, this Taylor series. So I, then the Taylor series for sine x. So you ended up with, oops, my whole thing just crashed. Yeah, my presentation crashed. One sec. Gotta recover it. This software does that. It has crashed on me before and actually I've lost everything. Sucked. So I save everything quite frequently. All right. So by putting in pi into this particular formula, Euler's formula, x equals pi, you end up with e raised to the I pi cosine pi plus I sine pi. Okay. The interesting thing with that is, if you guys remember trig, cosine pi is equal to -1, sine pi is equal to 0. 0 times 1, because 0 is the multiplicative identity, goes away, and you end up with e to the I pi equals -1, which you can just add 1 to either side and get Euler's identity, e to the I pi plus 1 equals 0. That's how you derive it. it's fascinating because there's such a beautiful relationship between ring theory and unit circle and identity and pi and natural logarithm, that all these things just break down into very simple formula like this: e to the I pi plus 1 equals 0. It is one of the most beautiful, most majestic formulas of all mathematics, I think. So real quick, I just want to show you that why how you would, if you wanted to go ahead and do this on your own, you could. If you want to figure out how to find the Taylor series for cosine x and sine x, you would start from this expansion, which again, go watch my video on Taylor series. But just remember that if the function is cosine x and the first derivative is negative sine, the second derivative is negative cosine, the third derivative is sine, right? I don't know of a way to memorize those other than rote memorization, right? If you guys that are really good at trig and calc might have a mental way of doing it, I don't have one. I just happen to remember that the first derivative of cosine is this negative sine. It's rote memorization. And then if you take the derivative of that again, cosecant. No, cosine, yeah. Just makes, I don't know where I got cosecant from. It's negative cosine, and then if you take the derivative of that, you get up at sine. So the function is cosine, first derivative is negative sine, second derivative is negative cosine, and the third derivative is sine. And you just put them in here, and you end up with cosine A, sine A over 1 factorial, cosine A over 2 factorial, sine A over 3 factorial. And then when you have A equals 0, which is centered around 0, again, we're going back to watch my video on Maclaurin series, which is a special type of Taylor series, you end up with cosine x equals 1 minus 0 over 1 factorial. You just zero out all the a's, and you're left with 1 minus x squared over 2x plus x to the fourth over 4 factorial. That's what I'm going to fix right now. There we go. Let me see if I can scroll down further, because you won't be able to see this unless I scroll down. And you end up with that. There you go. Now, again, you can check that on your own, and you can figure it out for sine if you want. But that's it. So I hope you guys enjoyed this. Again, I like doing things on the fly. I like using LibreOffice. I can fix things quickly, but of course, I'm going to make mistakes. I'm not a mathematician, nor do I claim to be. Take everything I say with a grain of salt. But, I do have actual PhDs out there that watch these things that are happy to correct me when I make a mistake or to try to explain things a little bit better. But I'm just trying to show that if I can understand it, you can understand it. And I find these things to be amazing. I really do. I think this is the most elegant formula involved in mathematics, just because of how it's derived, just because it has to do with a circle, has to do with radiometric decay, has to do with, so many different things that we see in nature. And a lot of it goes back to our discussions on dealing with teleological versus teleonomic, the appearance of design over, some actual intelligent design, which is something we've talked about on Agree to Argue, which is a show that I do with Dr. Fazrana, with Reasons to Believe, which is Dr. Hughes' organization. And so it all interrelates to each other, right? This is my whole point of doing this presentation. Everything we do relates to something else. We all relate to each other. And I think going into the year 2021, that should be our theme. How do we relate to each other? Because I want to relate more to the people that I've hold dear, the people that have been, an integral part of my life, the people that have been supporting me for, the 7-8 years I've been on YouTube now. I started my channel, I believe, in August of 2013. I didn't have my first video until like 2015, I think, early. But that's been, it's going to be 6 years of putting out content, over 1,000 videos. It's a lot. It's a lot. But I want to do things like this just because I find them to be fun. I find them to be entertaining. I find them to be educational for some people that may have never seen anything like this, right? A lot of people don't have the exposure to these things that we're accustomed to. I know, Abelian, I know Darth Calculus, I know Dr. Pi. All you guys have had maths. This is second nature to a lot of you guys. But you got to remember, it's not second nature to a lot of people that have not been exposed to math. And what these things are just intros. They're just presentations on a very intro level to get people exposed to these types of maths. So when they do learn about them formally, they have some basic conceptualization of them. I think that's kind of my point of doing these videos. It's not obviously to teach a class. I'm not a teacher. I'm not an instructor. I'm not here to solve your homework, because I suck at that. So don't ask me to do your homework assignment. I just want to get concepts across, because I find that people that learn concepts over rote memorization do a lot better in these discussions. I've seen people that think that they have rote memorization down that don't understand the concepts, and when you try to get them off their script and you try to get them out of their comfort zone, they just fall apart. And we see a lot of them on Twitter. But anyways, guys, I have my daughter coming over in about 5 minutes. She's going to spend New Year's Day with me, and that to me is how I want us to bring in the New Year's. Please be safe. Don't drink and drive, even though New Year's was tonight, but you're still partying all today. Just be safe about it. I will be doing a couple more presentations later on this week, or at least reading on my blogs. I'm going to be reading Dr. Pai's blog on hierarchy of rings and groups and fields. And I'm going to be reading my own blog post that I wrote on intentionalities. Trying to explain the difference between intentionality with a T and intentionality with an S, and and how it kind of works when it comes to propositions, and why I think these objectivists maybe don't understand these concepts, because they don't understand equality or equivalence very well. I don't know. It's just very bizarre. But what I did was I wrote a blog on taking their argument and looking at it from the best possible light that I can see, given principle of charity, which Cheshire and I have talked about. I've given principle of charity. It's the best argument I can come up with. It's still not a very good one for them, because they're still denying 0.99 repeating equals 1. They're still denying it. Even though, again, it's mathematically proven. It's conceptually not that difficult. But that's why I call them objective math deniers, OMDs, objective math deniers. All right, guys. Thank you very much. Thank you for all of your support. Thank you all for your donations and your patronage. And you remember, again, I'm going to be surviving on that in 2021. So I got to keep you guys happy. I got to keep you new math nerds and science geeks happy. At the same time, enjoy what I do. And I think this is the best way to do it, by doing things that I like to do, which is simple presentations like this, in 90 minutes or less. Okay. And with that, guys, good night.